Okay, qualitative treatment of liquids surface tension. It is defined as the force acting at right angle to the surface along the 1 centimeter length of the surface, unit Newton per meter in SI unit or dyne per cm in CGS. Effect of temperature on surface tension. The rise in temperature diminishes or decreases the surface tension of liquid. The decrease in surface tension with temperature is due to the fact that kinetic energy of molecules increases and the intermolecular attraction decreases with temperature. This decrease the inward pull or inward attraction of the surface molecules, and the surface tension becomes less and less with increase in temperature. Determination of surface tension of liquid, capillary rise method. Figure capillary rise method to increase the surface tension. Suppose one end of a capillary tube is immersed into a liquid. Then the force of surface tension pushes the liquid into the capillary tube to a certain height till the force of surface tension acting upward balance the weight of the liquid acting downward. The component of surface tension acting in the vertical direction equal to b cos theta. If the inner circumference of the capillary equal to 2 pi r, then the force of surface tension acting upward direction is equal to 2 pi r b cos theta. Weight of liquid acting the downward equal to mg equal to vdg. So equal to, we can write pi square s dg, b equal to pi r square h. G acceleration due to gravity at equilibrium to pi r b cos theta is pi square s dg. So we can write b equal to h r dg to cos theta. For most of liquid, theta equal to 0 and cos theta equal to 1. So equation 1 becomes b equal to r s dg over 2. Thus, these only two parameters that need to be measure one inner radius of capillary tube and height of the liquid capillary tube. Drop weight method. The weight of drop falling slowly through a capillary is directly proportional to its surface tension. When drop just falls, the downward force due to the weight of the drop is equal to the upward force due to surface tension. VDG equal to mg equal to 2 pi rv. So W equal to 2 pi rv, where V equal to volume of liquid drop, G equal to acceleration due to gravity, the density of liquid, 2 pi r, circumference of capillary having the radius r, B surface tension. From equation 1, we have W proportional V. If V1 and V2 are the surface tension, N of water and examined liquid, then W1, W2 equal to V1 upon V2, where W and W are the weight of the one drop of the water and liquid. If need, N1 and N2 are the number of drops counted in the same volume for water and examined liquid. So we can write W1 equal to B over N1 D1G and W2 equal to B2 over N2 D2G. Where D1 and D2 are the densities of water and examine liquid, substituting the value of water W1 and examine liquid W2 in equation third. So B1 over B2 equal to N2 D1 N1 D2. Viscosity and fluidity. Viscosity of liquid is the resistance to flow of liquid. It's called viscosity. For example, honey has a high viscosity because it flows slowly. Water has a low viscosity because it flows quickly. The flow of liquids through a pipe with different velocities in different concentric layers can be understood by the flowing figure. The longer line represents higher velocity and shorter line represents lower velocity in the figure. Figure flow of liquid in different concentric layers through a pipe. The liquid layers just adjacent to the wall of the tube is almost stationary and velocity of each layer gradually increases towards the center. The liquid layer flowing through the center is fastest. In this case, the slow moving liquid layer retards the speed of fast moving adjacent liquid layer. This retarding force is called viscous force, and dV be the difference in the velocity of adjacent layers. Then velocity gradient is dV over dx. According to Newton, the viscous force depends upon the following factors. Viscous force F is directly proportional to the area of cross section of tube. So F proportional A. Viscous force F is directly proportional to the velocity gradient dV over dx between the concentric layers F proportional dV over dx. From equation first and second, F proportional A dV over dx. So we can write F equal to neta A dV over dx, where neta is the proportionality constant and is called coefficient of viscosity. So F equal to N A dV over dx represents Newton's formula for viscous force. If A equal to 1 cm square and dV over dx equal 1 cm per second, then magnitude of F equal to neta, hence the coefficient of viscosity is defined as the viscous force operating between the two parallel plates is of the unit of cross section maintaining unit velocity gradient. Unit of coefficient of viscosity from F equal to A neta dV over dx. So neta equal to F dx A dV in CGS. Neta equal to 9 per cm squared. Cm over 9 per cm per second. So 9 second per cm, the poise. In CGS, the unit of the coefficient of viscosity is dyne cm and dyne second per cm square, which is also called poise. In SI unit, system neta equal to n over meter square, cm meter per second, Newton second per meter square. Okay, effect of temperature on viscosity. As temperature increases, the viscosity of liquids decreases because the molecules gain kinetic energy, move faster, and overcome intermolecular forces more easily. In contrast, the viscosity of gases increases with temperature because faster moving gas molecules collide more frequently, creating greater internal resistance to flow. Liquids higher temperature, lower viscosity, they flow more easily. Gases higher temperature, higher viscosity, they resist flow more. For example, when at room temperature is thick and flows slowly, but when the heated, it becomes runny, viscosity decreases. Effect of temperature on surface tension. The effect of temperature on surface tension refers to the way the surface tension of liquid changes as its temperature changes. Generally, surface tension decreases with an increase in temperature because higher temperature increases the kinetic energy of liquid molecules, reducing the cohesive forces at the liquid surface. Water at 0 degrees Celsius has a surface tension about 75.6 meter Newton per meter. Okay, water at 0 degrees Celsius has surface tension of about 75.6 millinewton per meter, while at 100 degrees Celsius it drops to about 58.9 millinewton per meter. Determination of viscosity by Ostwald viscosity meter. According to the Poiseuille's law, the volume B of liquid through a tube having radius R and length L under difference of pressure at the twin P with the time T given by B equal to pi PR4T over 8 neta L, where neta is the coefficient of viscosity, neta equal to pi PR4T over pi VL. Post-wall viscometer is dry state is taken. Initially, water is taken into the post-wall viscometer through the limb X. Then the water is sucked towards the limb Y up to cross the upper mark B, C, upper mark B. Then the liquid is allowed to flow down with the help of the stopwatch. The time flow of liquid from upper mark B to lower mark A is noted. The same process is repeated for 3 times and mean time is calculated. Then the viscometer is dried in oven and it is cooled. Then the liquid is under study is taken and time flow from upper mark to lower mark is noted as in the previous case. Let the time flow of the liquids from B to A be T1 and T2 respectively. Their coefficient of viscosities be neta 1 and neta 2 respectively. The difference of pressure at the two ends be rho 1 and rho 2 respectively. Sorry, P1 and P2. The volumes of liquids from upper mark to lower mark is fixed and radius of the tube is also fixed. Then using the equation second, for the first liquid, neta 1 equal to pi P1 R41 at BL. Equation third, for first liquid water, neta 2 pi P2 R42 at BL. Equation third is divided by equation fourth. So we can write neta 1, neta 2 equal to P1, T1, P2, T2. We know that pressure P force over area. So P equal to force mg over A. So P1 equal to BdG1 over A. Similarly, P2 equal to BdG dt2 G8 and P1 over P2 equal to D1 over D2. Where D1 and D2 are densities of the first and second liquid respectively. Now putting the values of P1 and P2 in equation fifth and neta 1, neta 2, D1, T1, D2, T2. So we can calculate neta 2, D1, T1 over D2, T2, neta 1. Application of viscosity. The knowledge of the coefficient of viscosity of different liquids is utilized for the selection of lubricants for machinery use. Knowledge of coefficient of viscosity may give the indication of extent of cohesive force hydrogen bonding, and boiling point. The condition of high blood pressure and strain of the heat can be explained on the basis of viscosity of blood in the arteriosclerosis, hardening of artery. The diameter of capillaries are decreased and offer resistance to flow of blood due to viscosity. At high fever condition, the viscosity of blood decreases due to increase in temperature. If concentration of carbon monoxide in blood increases, it returns in swelling of corpuscles and it increases the viscosity of blood. Okay, thanks for watching and request you all like, comment, share, and subscribe. Thank you for patience. Let us know. Bye bye. See you again.